Hi all. In this video, we will discuss about analytical learning in machine learning. Till now, we have taken many algorithms which comes under inductive learning. Inductive learning methods such as decision tree learning, neural network learning, genetic programming learning requires a certain number of training examples to train the system. Whereas analytical learning uses prior knowledge and subset of training data to train the system. As we discussed, inductive learning requires a number of training examples to train the system. We are using these training examples to train the system to achieve a given level of generalization accuracy, which reflects in theoretical bounds and experimental results. In the case of inductive learning, if you provide insufficient data, in that case, the system you are developing perform poorly. In inductive learning, we are learning inductively from a given number of training examples, which leads to fundamental bounds on the accuracy that is to be achieved. Examples for inductive learning are neural network learning, decision tree learning, genetic programming, genetic algorithms, etc. Whereas analytical learning uses prior knowledge and deductive reasoning. In the case of inductive learning, we are learning inductively. Here, in the case of analytical learning, we are using deductive reasoning to augment the information provided by the training examples so that it is not subject to the same bounds. Example for analytical learning is explanation-based learning. Here is the example for analytical learning. In this example, target concept is we have to design chess positions where black will lose its queen within 2 moves. Here, in the case of analytical learning, we require prior knowledge first. So what is the prior knowledge we require here? All the legal moves of chess coins. So here, by taking these legal moves, we can design. So that is white knight. We are taking white knight. So by using its legal moves, so either one horizontal and two vertical, or two horizontal, one vertical, like that. Okay. So we are keeping all other coins on the board. So here, by taking this white knight, we are placing checkmate to the black king, and the same time, by using this white knight, we can remove black queen. Okay. So as you placed you imposed checkmate on black king. So black has obviously has to move its king. So then in the next step, you can eliminate black queen by using white knight. Then one more thing we have to keep in your mind. So if you are keeping white knight here with any other coin of black, there is no threat to the white knight. So like that, you have to prepare your chessboard to meet our target. Same thing if you want to train in the case of inductive learning. So there we are not taking any prior knowledge. So step by step we are developing the system, okay, by using set of training examples. But in this case we are using the prior knowledge, which is all the legal moves. In addition to that, we are using deductive reasoning. So like that, you can easily develop the system by using analytical learning. So first we see the analytical learning. What is the input we have to provide for that one, and what is the output we are going to get by applying this analytical learning. So for this analytical learning, the input to the learner includes same hypothesis space H and training examples as for inductive learning. In addition to that, we are providing a domain theory consisting of background knowledge that can be used to explain observed training examples. So which is nothing but prior knowledge. Next, the output. What is the desired output of analytical learning? So, what is the hypothesis you are developing by using training data, subset of training data, and prior knowledge? That is to be consistent with both the training data as well as domain theory. Otherwise, if that is not consistent, the output which is generated by using this analytical learning is not valid one. To discuss Prolog Ebg algorithm under explanation based learning, we are using safe to stack example. In this example, we are designing a system to check to place one object. Is it possible to place one object on other objects? So to gain the target concept, to train our system to get the target concept, safe to stack of x comma y, that is x object, is it possible to place on y object or not? So here we are providing instance space, hypothesis space. So instance space. So each instance describes a pair of objects by the predicate. What is the type of that one? What is the color of that one? So what is the with which material that one is made, like that. Then hypothesis space. So here using many predicates, so less than, equal, greater than, and we are using many functions, plus, minus, and times. Okay, so like this we can develop this ones. Okay, this is the target concept. So we are getting that one by using conjunctions of literals, using on this one conjunctions of literals based on some same predicates used to describe the instances. So here volume x comma vx, volume y comma vi, so less than vx comma vy. So in that case x1 you can place on y1. Okay, so for this analytical learning, you have to provide training examples as well as you have to provide domain theory. By using these two, we have to develop one hypothesis that must be consistent with both training examples and domain theory. So, what is the domain theory you are providing to your algorithm? That domain theory must be correct and complete. So, what do you mean by domain theory must be correct and complete? So, here when you can say the domain theory is correct one, if each of its assertions is a truthful statement about the world. Next one, when you can say it one is complete. Domain theory is a complete one. So a domain theory is said to be complete with respect to a given target concept and instance space. If domain theory covers every positive example in the instance space, then it is complete one. So to develop this one, your domain theory must be correct one and complete. So now we will start our discussion with the Prolog Ebg algorithm. So it is also a sequential covering algorithm which considers the training data incrementally. So here, for each training example, for each positive training examples that is not covered by the horn class, in that case, it has to prepare new horn class. How to prepare? So by following these three steps. First, explaining the training example. After that, we have to analyze this explanation. So whether to determine it is appropriate generalization or not. And refining the current hypothesis by adding this new horn class rule to cover this positive example as well as other similar instances. So briefly, we are adding horn classes to the set which covers new positive examples. We have to continue this process until no other positive example is left out. So first we will see the explanation on training examples. So here we are taking two training examples. So here object one is object one and its properties, and object two its properties. So that is a training data we are considering. So from that we have to explain our training examples. So here we are finding the weight of object 1 as well as weight of object 2. Our main task is to check, is it possible to place object 1 on object 2? So when you can place, if object 1 weight is less than object 2, you can place that particular one. So this is only one criteria. Later we will take the volume also like that. So here you are observing object 1 volume, density. So all are properties already considered, already present. So we are taking calculating weight of that particular one by using these two. So like that we got weight as 0.6 object 1. Then we are considering a second object. So that in that one we have taken as end table. We predefined its value prior knowledge. Its value as 5. Weight is 5. So we are comparing these two weights. So automatically this 0.6 is less than 5. So we are concluding that object 1 is lighter than object 2. So when this is satisfied, you can place object 1 on object 2. So like that we have to provide explanation on the training data. This Prolog Ebg algorithm considers training examples incrementally. For that, it uses a general procedure called regression. Here, Prolog Ebg computes most general rule by computing the weakest pre-image of the explanation. What is this weakest pre-image? So that is for all the assertions. First it considers one initial assertion. So what is that initial assertion? So that is, for example, here you can observe that one volume, x volume, x object volume, x object density, and you are calculating its weight and other object weight, and that is end table we are considering. So these are initial assertions. Okay, so we are taking a conjunction of all these initial assertions. By considering only these, it is not possible to come to one conclusion. So we have to perform further refinement on these assertions. So in this case, the initial assertions, conjunction of initial assertions is the first weakest pre-image. Okay. So here, this initial assertions is entails next conclusion. So the weakest pre-image of the conclusion with respect to proof P is the most general set of initial assertions A such that A entails C according to that particular proof. Okay, so without A, it is not possible to get the final conclusion. So these are the basic data we are considering, basic training data we are considering. So by using that, by using these things, we have to develop the system. So this is the initial thing. So by using this, we have to develop the conclusion. Here, Prolog Ebg computes the weakest pre-image of the target concept with respect to the explanation using a general procedure called regression. So that is step by step we are performing. First initial assertions we are taking. So by using that next step, what are the positive examples are required for that one. So like that, finally we are going to the conclusion phase. So here main thing we have to consider is procedure, regression procedure. How this regression works? Regression works iteratively backward through the explanation. So first it computes weakest pre-image of the target concept with respect to the final proof step. Then computing the weakest pre-image of the resulting expressions with respect to the preceding step and so on. It continues its process until it has iterated over all the steps in the explanation. Here, the heart of regression procedure is the algorithm that at each step regresses the current frontier of expressions through a single horn clause from the domain theory. So first we have to consider this one. So we'll take one example how this regression proceeds. So here how this regression is carried out. So initial premise, what we are considering pre-image is this particular one. Okay. So here we are taking weight of y objects and we are calculating weight of x object. So that is object 1, what is the volume of this one and what is the density of that one. By using that we are calculating the weight as 0.6. So here y object, object 2, we are considering as end table. Its weight we are considering ywy. At present, we do not know that particular one. See here. So in between these two, I have to perform this less than operation. So from this step, directly we are going to this particular one. Next step. So a weight of object 1 we got. Similarly, we have taken weight of object 2 also. Then we are performing less than operation. So that is we are comparing those two, 0.6 comma 5. So which leads to lighter of x comma y, lighter of object 1 comma object 2, which again leads to, so this one is satisfied. Once that one is satisfied, our final proof, final target concept we reached. So this is iterative process. Step by step it carries. So here we'll discuss about regress algorithm. So one example for that one. So first, in the case of regress, first what we have to take, we have to take the frontier. So what is this frontier? So in the bottom level, all the leaves what are present in our example, we are considering as frontier. So from next step onwards, we have to we have to try to reach the destination. So what is the rule we are considering? That is one Hahn clause. That is end table weight is 5 we are considering here in this case. So then what is the literal we are considering? So that weight we are calculating, that is Wy. So that one we are taking as a y here. So what is the rule we are providing? So that one gives our literal value. So here, what you need to be substitute. So here that is we are writing by HI like this. The substitution that unifies the head of the rule to the corresponding literal in the explanation. So next one, see here. So head we have to consider. So wage z comma 5. So z we are replacing with finally with y like that. Okay. Then what is the body we are considering? Type z end table. So here we are calculating, we are taking that substitution. So z with wy. So z with y, wy with 5. Okay. So here next after that we have to return. What we have to return? You observe here. So that is frontier minus head plus body. So you observe in the frontier what we have taken initially. These 5. Okay. So minus head. What is head? Weight z comma 5. So what is the body you are adding? So type z end table. So but in our case z we are replacing with y. So that is y end table. So finally we are this one we are replacing with y end table. That means what is the object type we are taking? We are taking that one we are replacing with the end table. So that is the one level for the leaf level to the next parent level we are going. So this is the regression procedure. This procedure is iteratively performed until you reach the final goal, that is target concept. So here is the Prolog Ebg algorithm, which is almost similar to sequential covering algorithm. So what are the what is the arguments we are passing to this algorithm is target concept, training examples plus domain theory. So initially our land rules is empty set. Then POS, that is a positive set of example. All positive examples we are taking from training data. So for each positive example, and what are the rules are not covered, that is not covered by the land rules. So for each positive example, so first step, explanation. Okay, so explanation case, okay, what is object properties, what we are taking, so by using domain theory. Okay, so in terms of domain theory, like that. So explanation in terms of domain theory, that positive example satisfies the target concept. After that we have to analyze that particular one. So for that analyzation we have to consider sufficient conditions. The most general set of features of positive example sufficient to satisfy target concept according to the explanation. After that, last step is refinement. So refinement is the rule which satisfies, which cover the positive example. Okay, so that rule we have to add to our land rule set. Initially we are taking land rule as empty set. So by considering each positive example, so the land rule, okay, the rule which satisfies that positive example, we are adding to the land rules. Okay. Until we have to repeat these steps until no positive example is left out. So after that, finally we have to return land rules. So this is the algorithm, Prolog Ebg algorithm, which comes under explanation based training, which comes under analytical learning. Thank you.